Hello everyone, in this video I'll be talking about built-in delay functions in MPLAB. This video is in a way continuation to my previous video about oscillators, since the frequency plays an important role when it comes to delay functions. But that video was getting a little too long, so I decided to separate them. If you don't care about the explanations and just want to see the functions, you can skip to any part of the video using timestamps in the description. And I mean this, because I'll explain everything about delays so you won't have any doubts about anything, which also means I'll get into some math as well, albeit nothing complicated. So if you only care about the delay code in MPLAB, I recommend skipping to here, since this will take a while. So, let's get started. People that have Arduino background would know that there's a delay function you can use to stop the Arduino from doing anything for a given time. MPLAB also has this delay function, but be careful, this delay function does not come with your microcontroller. In fact, no microcontroller has a magic delay instruction. They just have a do nothing instruction, which we'll get to in a bit. In reality, delay functions are just a loop with no code inside that will loop for a given time. I've said multiple times that microcontrollers operate on each clock edge, meaning on each clock edge an instruction will be executed. There are some exceptions, but we won't get into that. If we know the frequency of which these instructions happen, we can also find how long an instruction takes. You should know that frequency refers to the rate of which something occurs. For electronic signals, frequency refers to the rate of which each repeat of a periodic signal occurs. This is commonly referred to as a cycle, by the way. So, frequency means how many times per second each of these cycles happen. The unit of frequency is hertz, which is 1/second. So, for example, 64 MHz clock signal refers to a signal that is switching 64 million times per second, which also means 64 million clock edges per second. You should also know that a period is how long it takes for something to happen, which makes it the reciprocal of frequency, and it has the unit of seconds. So for periodic signals, you can find how long each cycle takes if you know its frequency, and vice versa. So from the previous video, you should know that this microcontroller divides the system clock by 4 to get its instruction clock. If we assume that each instruction takes one instruction clock to execute, and the microcontroller is running at 64 MHz system clock, can you calculate how long one instruction will take? 64 divided by 4 gives us 16 MHz, which is the frequency for the instructions. This means that this microcontroller executes 16 million instructions per second. To find how long each instruction takes, meaning their period, we can just flip this term, which will give us the period of each cycle, thus each instruction. Remember that the unit of period is seconds, so it takes 1/16 million seconds for each instruction to execute. Now, if we can make an empty loop that takes a known amount of instructions to execute, we can generate any delay that we want. So, for example, if we wanted a delay of 1 second, we can just make an empty loop that takes 16 million instructions to execute. And that is exactly what the delay functions do. Delay functions in MPLAB are built in, and you don't need to include any libraries. This is the syntax for the delay function in milliseconds. If we control-click this function, it brings us to the built-ins.h file. Which makes sense since, again, they are built-in functions. It's a pre-built function in MPLAB, hence the name. You have 4 built-in delay functions in total. Actually, you only have 2 built-in functions and 2 macros, which are all defined here. The first one is __nope function, which you can also type like this. If you click it, you'll see that it's defined as the same. This function is actually an assembly instruction equivalent, which is also called nope. You may remember it from that other video. This function just spends an instruction cycle doing nothing. So for example, if I put 10 nope functions back to back like this, the microcontroller would do nothing for 10 instruction cycles. Then you have this _delay function, but you won't see this being used directly all that often. The value you put here is the amount of instructions to delay. So if I put 100 here, the compiler will generate the code needed for the microcontroller to do nothing for 100 instruction cycles. Now, the use of these two functions are not as common, since none of them use time as their unit. They just delay an X instructions amount of time, and how long that takes is dependent on your clock. The next 2 delay functions use 2 underscores as opposed to one used here. The delay ms and delay mus functions, as their name suggests, delay the microcontroller in terms of milliseconds and microseconds respectively. But these functions use time as their unit, meaning the compiler has to know how long an instruction takes to calculate the required instruction amount to achieve this delay. If we go back to the built-ins.h file, you can see the calculations needed for that. Let's try an example to verify this calculation on the milliseconds version. Let's say we want a 1 second delay. You know from before that this should take 16 million instructions when using 64 MHz clock signal. This function calculates the instructions needed to achieve this delay and calls the underscore delay function to generate it. The instructions calculated will be x times this term divided by 4000. This term refers to your system clock, so it's 64 MHz, which is 64 million. And x is the value you pass on to this function, which is your target delay. To generate 1 second delay, you need to pass 1000 here, right? Since this is in terms of milliseconds. And as you can see, this term does indeed equal to 16 million. Where does this 4000 come from? Let's rearrange the equation like this. This division by 4, as you can probably guess, comes from the fact that we are calculating the instruction frequency. And the 1000 here comes from the fact that Hertz has a unit of 1/2, so we need to convert that into milliseconds, since this is a delay ms function. So this term is how many instructions are executed per second, and this whole term is how many instructions are executed per millisecond. If we multiply this by the delay we want in terms of milliseconds, we'll get the amount of instructions needed. Let's also do this equation in terms of units, and hopefully it will be more clear to you. I'll denote the unit of instructions as just I. So the unit of this frequency term would be I per second. The unit of this term would be seconds divided by milliseconds. Don't forget that 1 second is 1000 milliseconds, hence we are dividing by 1000. The x here, as you know, is the delay we pass on to this function in milliseconds, so it will have a unit of milliseconds. The result should have the unit of instructions, right? If we do this equation, we indeed get I as the result. The equation for delay mus function should be self-explanatory. The only difference is this term. Just replace milliseconds with microseconds, which will make this term divide by 1 million instead, and there you go. You can also see the same on the definition of the function as well. These are all of the delay functions available to you. Let's go over again for people who skipped to this part. Nope function delays the microcontroller for 1 instruction cycle. Underscore delay function delays the microcontroller for X amount of instructions, which is the value you pass to it. So, underscore delay 100 would delay the microcontroller for 100 instructions. The next two are delay ms and delay mus, which delay in terms of milliseconds and microseconds respectively. Now, these two functions you can use without doing anything, since they don't use time as their unit. But for these two, you need to define this term called underscore xtel underscore frec. This term is needed for the MPLAB to calculate the time needed for each instruction, so it can generate the delay. This value should be your system clock in terms of hertz. So, if your microcontroller is running at 64 MHz, you would put 64 million here. If you don't, you'll get a compilation error. I usually put it in the config.h file at the bottom, but you can put it anywhere you want as long as it's defined in the file where you're using these two delay functions. Now, let's go back to our first example. Here, I'm turning the LED on and then waiting for 1 second, then turning the LED off and waiting for another second, on repeat. And of course, I have this xtalfrec term defined in the config.h file. If I program now, you can see that the LED is on for 1 second and off for 1 second on repeat, no problem. Now, what do you think would happen if I instead define this xtalfrec term as half of my system clock, so 32 MHz? Let's see. As you can see, the LED is turning on and off twice as fast. This is because the microcontroller is running twice as fast compared to what we told MPLAB, which means the delay functions are also executing twice as fast too. This is a way for you to test if you configured your oscillator block properly and if it's running with the frequency you intended. And of course, the reverse is also true if you doubled the xtalfrec term instead. Blinking would be twice as slow. Now, before we end, there's another important thing you should know. Say you want to generate 1 second delay. I said that you would need 16 million instructions, right? But the compiler doesn't just put 16 million nope instructions to do this. That would just be stupid. You only have 65,000 programming spaces to begin with for this microcontroller, and that is way more than what you would typically get. So instead, it generates an empty loop that will take 16 million instructions to execute. You can always check out how the compiler does this by reading your assembly code, which I showed you in a previous video, but that's not important right now. What's important is that, for the compiler to decide how to generate this loop, it has to know the delay amount you want prior to compilation. Because of this, you can't put a variable in the delay functions, or you'll get an error like this. The value you put here has to be constant, but there's a way to get around this. You can just put a small amount of delay like 1 milliseconds, then put it in a for loop like this. This way, you can make this delay last longer or shorter by changing this value right here. The downside being, this for loop itself will also take some time to execute, which means the delay you're generating will be less and less accurate the more you loop here to generate it. Before ending this video, I want to commentate on the usage of delays, but you can skip this part if you don't care. There won't be any more information about delays themselves. Ideally, the use of delays should be as minimal as possible. Most of the time, microcontrollers only have one core, meaning you can only execute one code at a time. So when you use delays, you're pretty much doing nothing, but the microcontroller is still running and consuming power within that empty loop. You can instead use timers, which are a separate module, to generate this delay, and go on to execute the rest of your code. And when the timer kicks in, you can execute your other function as you like. Also, this circuit as it stands draws 15 milliamps, even when disconnecting this LED. That may not seem like much, but when powered by batteries, 15 milliamps of constant drain would add up to be pretty big. When you need big delays like this, and when you don't need to do anything in the meantime, the better way to implement this would be to use a timer and sleep mode. You can use this command to put your microcontroller in sleep mode, which will drastically reduce the current consumption, as you see on the multimeter. And you can implement your delay using timers, which will wake up the microcontroller automatically. We'll talk about all this in the future, but long delays like these are typically not good practice. But if you're running off of mains, or just don't care to put in extra time for efficiency, that is of course fine. Just something to keep in mind. And that's the end of the video, and thank you for watching. If you liked the video, you can always leave a like and subscribe. It's always appreciated, and I'll see you in the next video.